Swayam Prabha, free DTH channel for education.
Right. So in this Zoom class, what we would do is we would we have in a way discussed about both DTFT and DFT, because if you notice, you have a continuous time Fourier transform which we discussed in very detail, and the moment you are taking samples on the time domain, right? So let's talk it as time domain and frequency domain for the time being. So the moment you are taking samples on the time domain, that is equivalent to which kind of transform you would be getting eventually. We have a continuous time signal, right? We have a Fourier transform of it that we have discussed. Now you are taking samples, just very trivial questions I am asking, so I'm expecting some response. Okay, you are taking samples on the time domain. It's equivalent to what? Which transform?
DTFT, sir.
DTFT, right? And now, in addition to taking samples on the time domain, I am also taking, so the moment I am taking samples on the time domain, what will happen to the earlier continuous time Fourier transform frequency spectrum? What is the one important thing happening there?
Repeated copies are present.
Right, good. So that is becoming periodic. Now, what is the periodicity of it?
2 pi by t.
No, that is where that's where the samples, okay, omega is equal to 2 pi by t, you are saying, right?
Yes, sir.
Okay, so that's where you are keeping the copy, but periodicity is not that. That only tells you where you are keeping the copy. Okay, yeah, for the time being, don't worry about aliasing part. You just think that you are taking samples here, right? And the moment you are taking samples here, you notice that it is becoming periodic. What is the periodicity of it? So, in other words, the Fourier transform for a discrete time sequence, what is the periodicity of it? Hmm? No, I am sure you all know probably the way it
2
is.
pi.
2 pi, that's right. So you might be keeping a copy at 2 pi by t, but periodicity, what you are getting is it is periodic with a periodicity of 2 pi, right? Good. But in terms of our medical imaging notations that we are not using omega. We are using frequency as f, which is in hertz rather than radians per second. So what is the periodicity now? For the DTFT?
1.
1. Very good. That's right. So earlier you would be writing minus pi to pi wherever you are writing your DTFT. What you would be getting now there? The limits of your integration. The moment you are moving to the frequency to the in the frequency domain for a discrete time signal,
Minus half to half.
right? Minus 1 by 2 plus 1 by 2. That's one change that's happening, right? So now, in addition to taking samples of the time domain, now in addition you can't keep track of all the frequencies. It's not possible when you are programming. It is enough to reconstruct the original, assuming again now. So earlier implicit assumption we made is the sampling is good enough to retain to cause no aliasing. Okay, that's the assumption there. Now another assumption we are now making is if your signal is a finite length sequence, okay, and again the number of sequences that you have, and you are taking at least those many number of samples of the frequency domain. Now what will happen to the inverse of the Fourier transform that you compute for this discrete samples? Will it also become periodic now? Hello? So now the earlier one was we took samples on the time domain. Now, in addition to that, despite taking samples on the time domain, its frequency domain is continuous time. Now I'm taking samples of this frequency domain, which is continuous now. Yeah. Samples of you have time domain, you took samples that gave a frequency spectrum, which is still continuous. You won't be able to do much with that in a computer, right? Where you are storing at only discrete points. So you took samples of that. So what would be the implication when you are taking inverse transform of that?
It will become periodic, sir.
It will become periodic. And if your n value is less than the length of your original signal, there will be aliasing. Okay?
Time domain aliasing.
Right, time domain aliasing. Earlier, there could be a frequency domain aliasing. That's all. Actually, we have in a way covered both DTFT as well as DFT. The initially started with CTFT. The moment you took samples of the time domain, that what you resulted is DTFT. And the moment you have in addition also taken samples of your frequency domain and restricted yourself to just one period. Okay, one period here is n being the number of samples of your original signal. So that case, what you are getting is DFT, right? In conceptually, we have in fact covered, by the time we finished both sampling of the time domain and frequency domain, in fact, we have covered both DTFT and DFT. But for the sake of completion and also for the sake of more clarity and doing a mathematical treatment of the same, what we would do in this class is we would write equations for both DTFT and DFT, both in 1D and 2D. That's what we will do. So what I want you to do also is have your pen and paper with you, write along with me, okay, work out along with me, so that otherwise if you just look at it after some point of time, looks like there are too many things are here, but once you do yourself step by step, there is nothing to remember there. Everything flows very smoothly, right? That's what we will do now. Okay, I'll share my screen, and I want you to also, every one of you, to do the same along with me on your notebooks. Okay, so what I'll do now is share my screen. Just to begin with, since I will not start from 1D CTFT and all, just let's write first for what is the expression for 2D CTFT. I'm sure you all remember it now because you had an exam also on that. So wait a minute, hopefully it should work smoothly, right? Yeah. So on what was the notation on the symbol we are using for the spatial domain? That was f of what was it that we were using? X comma y, right? And the CTFT, please write along with me as I mentioned. CTFT of it, we were denoting it by capital F here. Instead of kx and ky space is what we refer to the frequency spectrum of that, correct? Now, what's the value of f of xy? Well, both are continuous, so you have integrations here. Limits of this integration are from? Limits are from? Yeah, you need to go in a fast pace. Otherwise, we will not be going the entire thing. Yes, f of x, what are the limits of these integrations?
Minus infinity.
Yeah, that's all right. Minus infinity to plus infinity. And here also. Yeah, tell me what I will get inside. What would I get here?
F of kx, ky.
Ky, right? Into?
Exponential of j omega.
No, sir. We were
J
already
times 2 pi. Yeah.
right. J times 2 pi.
kx into x plus ky into y.
Good. And what about the expression for capital? I hope this will not obstruct me. Okay, that's better. So f of kx comma, let me put it slightly below. Right. Now, what was the expression for f of kx comma ky now? Minus infinity to plus infinity now. Sorry, what were the very integrating with respect to d kx and dky, is it not? So now you do it with respect to x and y. You have f of x comma y exponential of minus j times 2 pi kx into x plus ky into y, integrating with respect to x and y. Right. Now, what we would do now is, let's do it for one-dimensional DTFT. That's what, since this is all you are familiar with, and now since anyway you will be telling it to me now. So first we will also start here with what we did in our DSP course. As usual, we will start from there. What was the expression? So what were the variables we were using there? X of n on the Fourier on the time domain, and here we were using x of the DTFT of it. We are using as x of
e power j omega.
good. And what was the expression for x of n? X of n equal to summation or integration?
Integration.
Integration, or which period?
Minus pi to pi.
Right, minus pi to pi or 0 to 2 pi over a period of 2 pi. And here what will I get inside? X of e power j omega into e power
J omega n.
j omega n, and integrating with respect to d omega, is it
D
not?
omega.
Right. So what all changes we are doing the moment you are coming to our MI course here? X of n, let's call it f of x, okay? And since it is now discrete, the moment you are coming to discrete, we are using this square. So let's call it as f of m here, okay? So that later we call it as f of m comma n. And let's call the DTFT of it as capital F. This is still a continuous one, so let me call it as kx. Right now, so we are going to change the variable omega with what? Omega equal to what we are going to substitute here? Omega equal to, in order to get the new equations, what is it that
X.
2 pi kx.
2 pi times kx, correct? So that means your d omega will be equal to 2 pi times d subscript kx, right? Now, if your omega equal to minus pi, now what is your kx value?
Minus half.
Minus, right? Similarly, so you just need to substitute in the above omega equal to 2 pi x, that's all. So of course, then omega equal to pi means your kx equal to 1 by 2, correct? And what else is going on here? So d omega, you get there. Did I miss something in the earlier expression? Oh, I have, yeah, I have not written something there. I missed something in that expression.
By 2 pi.
Yes, there is a 1 by 2 pi here. Okay. And another thing is, I did not write the expression for x of e power j omega. So that also, let me write that. X of e power j omega equal to x of n. In terms of that, I am going to write, because that being discrete, I write x of n. Earlier e power j omega n is there. Now I have e power minus j omega n, and this n could vary from minus infinity to plus infinity, right? So now you tell me the expression for f of m now. See here, omega, you 2 pi into, you substitute dkx, so 2 pi gets cancelled out. So that constant is no more there. Integration varying from -1/2 to +1/2. And in place of x of e power j omega, I have f of kx and e power, what do I get here now? E power j times,
2 pi kx.
that's all, 2 pi kx, and integrated with respect to dkx. Is everyone with me? Or any questions so far? And then
M value,
yeah, hello,
M value in this expression, sir.
m value,
E power j 2 pi kx into m.
no, sorry, I didn't get you.
In the f of m expression, sir.
F
For
of
what m?
f of m expression.
Sir, on the exponential, you have to put j2 pi kx into m.
Yeah, very good. Sorry, that's your right. Okay, that's right. 2 pi kx into m. Now, what happens to f of kx now? This is again a summation. Your m varies from -infinity to +infinity. F of m into exponential of minus j 2 pi kx into m dk. Sorry, why there is here? That's what, when you are copying blindly, this is what would happen, right? Is that fine? Is everybody okay with this thing? Right, this just that this has changed, and this also just like CTFT, the moment we move to the frequency kx, that normalization factor is not there. So this is also very nice. So now here, one thing to note here for you is, what is the periodicity of this function now? What's the periodicity?
1.
1, correct. So I could actually write then f of kx plus any integer p is equal to f of kx, where this p is any integer, right? Because anyway 2 pi is here, so even you could see here m plus 1, if you take e power k, then you have this integer multiple there, right? And so f of kx plus p will be there, and periodicity is equal to 1 here, right? Now what we will do is, with this background, let's call this as one dimensional DTFT. Okay, now let's write expression for right away for two dimensional DTFT. Now we already right away for this course we'll write, there is no reason for again two writing. So we already made adjustments to our notations already to extend it to 2D. So this is straightforward. Instead of f of m, now you have f of m comma n here, and the DTFT of it you are going to call as f of kx comma ky. Right, now you write the expression for, yeah, can one of you tell me the expression what I would get here? F of m comma n equal to,
Integration minus half to half.
right, good, minus half to half,
Integration minus half to half.
right,
F of kx comma ky.
right,
E
explain,
power j j 2 pi kx m plus ky n.
very good. Is everybody with me?
Dkx dky.
That's it, that's all. Now what is the expression for f of kx? I'll just again write it slightly below. F of kx comma ky would be equal to, similarly,
summation of
Hmm.
minus infinity to infinity,
Hmm.
summation n equal to minus infinity to infinity,
Hmm.
f of m comma n
Hmm.
e power minus j 2 pi
Hmm.
kx m plus ky n.
Hmm. That's all, right?
Hmm.
Yeah. Any is everybody able to follow that? Otherwise, please don't hesitate to just stop me here. We would just get because once you understand it clearly, there is nothing to remember. Otherwise, if you are not following the thread, it looks like too many things are going on here, and it looks pretty abstract because there are only equations we are writing here. Okay, is that clear to everyone? Okay, I hope then it is clear to everyone. Now, what's the next step for us to graduate after 2D DFT, 1D first started with 1D DTF, okay? 2D CTFT we just written, 1D DTFT we have written, then we have written 2D DTFT. What do you want me to write now?
3D.
3D, yeah? No, I mean, we will go to 1D DFT, okay? Right. So again, we will start with the DSP course notation where we use what were the variables we were using there. On one side, you have x of n, and the DFT, you had x of k, and x of n. Again, you assume that I'm not explicitly writing here, but x of n you have is not equal to or non-zero for 0 to n minus 1. So its length is n. That's what we are assuming there. Okay, I'm not writing all those things, but you know it. Okay, now how do you express x of n in terms of x of k?
Summation from 0 to n minus 1.
Summation of what is the variable here? Summation
K.
variable is
K.
k, 0 to n minus 1. Then
X of k
hmm,
exponential of
hmm,
j
hmm. Then
2 pi
hmm.
2 pi n by 2 pi small n by capital N.
Right. So the duration of it is periodic with periodicity 2 pi, and you are making it into divisions of 2 pi by n, right? The distance between each division is 2 pi by n. If you are, see, you have a periodicity of 2 pi, you are making it into n divisions here. So what would happen? This length would be equal to 2 pi by n. So that's why you are taking 2 pi by n multiplied with
Small n.
yeah, small n and also k.
K.
Right? Is that all? Is there anything missing here? At least
1 by n.
right, 1 by n is also here if you remember. Okay, hope you all also remember how we arrived at this being periodic. We started in our course with DFS actually while doing it. Anyway, that's just a mathematical detail, so that time you easy to figure out why you get 1 by n there. Okay, now you tell me the expression for x of k, n varying from 0 to n minus 1, x of n e power minus j 2 pi by n times k n. Is it not? There is no more multiplication factor or anything here. Now let's go to how we adjust it for the medical imaging course. F of L, we call it as, how are we calling on this side? F of m comma n, right? We follow the same notation here. Let's call it as f of m here. so that I'll write later f of m comma n. And the DFT, well, that is also now discrete. So capital F of, let me call it as something like u here. Okay. Then here also let length of the signal be capital N, or maybe since I used small m there, and later while going to 2D I call it as small m comma small n. So I let me call this length as capital M here, length of the sequence. Now with that change, then my f of, what should I write now? F of m is equivalent to, what is that? Tell me now. F of m is equal to, there is not much of a, not many things to be done here. It's actually quite straightforward here. F of m equal to, hello,
Sigma n equal to 0 to capital N minus 1.
sigma,
M minus 1.
sigma, what is it I need to change here?
N equal to,
Yeah, I'm using u there, so let's use the same thing.
okay,
Okay,
that's U. Okay.
u equal to,
U
yeah,
equal to 0
it
to
is
n
not
minus
looking
1.
like u, u
Yes,
equal to
yes.
0 to
M minus 1.
okay,
F
and
of
then
U
uh,
e power
uh,
j
hmm,
2 pi by m
2 pi by m, good,
mu.
very good, that's all.
Small m, small u.
Yeah, not looking like that.
And at the outside, it's put 1 by m.
1 by
Right, correct. This is there. And then what is the expression for f of u now? Very similar lines, right? This is quite straightforward. F of u would be equal to, what is the variable now here in summation? Let's call it as m, because there we are calling it as m, into small f of m into e power minus j 2 pi by m into mu. Is everybody fine with this? Hope you all following the thread here. Okay.
Yes, sir.
Yeah, good. So let's do the final workout now. Okay. So the last one, two-dimensional DFT. Okay, with this we are done. Right. So we have purposefully written that as m there. Now it should be pretty straightforward. We call it as m comma n. Okay. And then the DFT is equal to capital F. Let's call it as u comma v here. And this, should the lengths of m and n be same? But
not necessary.
not necessary. What is it that would decide how, what should be the values of m and n? Is
The
there
height and width
something?
of the image.
Is that height and width of the image that decides this m and n?
Sampling and quantization.
Right. See, in fact, that is also, both answers are in a way correct. See, yeah, m and n is basically are essentially the maximum values are height and width. That's also correct. Suppose, yeah, because you want to find finally the inverse transform also should give you an image. So basically, if you have an m by n image, finally inverse DFT also should give you. So I agree with the answer that in general you could say it as height and width of the image. That's fine. Otherwise, if you are doing some low pass filtering and taking a different length of inverse transform, that those kinds of things also could be done. Okay. So anyways, so this length, let's assume that this is m, this length, you assume that n. Okay. Now we write the expression for, to begin with, f of m comma n. Tell me what is the multiplication factor here outside.
1 by mn.
Very good. This is equal to 1 by mn. Now there are two summations here. Let us call first one, let's say u varying from, let's say, assume that m and u are related and n and v are related. So u varies from 0 to
m-1.
right. And v varies from 0 to
n-1.
right. Very good. And then inside, okay, hope it is not looking like capital F. So let me use this out. Okay. So this inside I have f of u comma v. Yeah, this you have to carefully tell now. Exponential of, okay, j times. Now you tell me what should I write?
2 pi whole into
Very good. Then
small m by capital M times u
right. Then
plus small n by capital N times v.
small n by capital N times v. Very good. Is everybody with this? See, it's simple. Now you, instead of m here, you have for one case capital M and another case capital N. So that's 2 pi is anyway common. So that is taken out. M by m into the corresponding variable here is m and u are related. So mu by m and nv by n. Right? Hope everybody is able to follow that. Then capital F of u comma v, once you write this, this is pretty simple. You just get rid of the multiplication factor, change the exponential sign, is it not? And of course, change the variables here. Instead of u and v, you have here m varying from 0 to m minus 1, n varying from 0 to n minus 1, then f of m comma n, right? And exponential of minus j times 2 pi into mu by capital M plus nv by capital N. That's all. Okay, so if you follow this and if you remember these basics correctly, this is quite straightforward things. That's all. We are done with writing all these things. Sampling part anyway we discussed. So with that we are done with all the transforms and their definitions we are done with. Sampling part anyway we have already covered in the last couple of lectures, right? So all we would be doing is just one more. Let me just stop sharing and come to the video. Okay, so with that we are done with this. So what I will do in just one more class, mostly I will make a recorded presentation. This I thought writing equations, it would, you may feel more comfortable if we are doing along with you in the Zoom session. So I didn't made a video for it. So hope you are able to follow that. But anyway, central cross-section theorem, that's one important theorem, comes from the Fourier domain, which essentially tells you that suppose you have a projections of 2D available to you, of a 2D Fourier transform are available. So projection of 2D Fourier transform means you have a set of 1D Fourier transforms. So the question would be, from that, will you be able to construct back the original signal? That's the essentially the problem you would be able to, we are going to look at. Okay, that's what I will most likely share a video with you by Monday. And Monday's class would be the last one on frequency domain analysis. With that, we will move to some other topic. Okay. Yeah, so that's all. We are done with this class. Any questions? So whatever has been covered so far.
So regarding the 2D DFT, the lengths M and N.
Let me then go back here. Yes, the lengths M and N here.
Yeah, so like you said, like we normally the upper limit for M and N is the dimensions of the image, right? But suppose we have some periodic pattern in the image. So like if we consider just the length of the first period of the pattern, will that give the correct DFT?
See, look at it this way. The moment you have an image, it has been sampled from the continuous time domain, correct? So if there was already an aliasing in the frequency domain because of the sampling, there is nothing we could do about it. It is possible that by the time you got the image itself, there is some frequency domain aliasing, because an image is essentially a discrete time signal, correct?
Yes, sir, possible.
And then all you are doing now is that frequency domain aliasing, you don't have any control, but spatial domain aliasing is what you need to take care into. And further to not happen, if you have a discrete time signal, you just need to take number of samples you take on the frequency domain should be same as whatever number of samples you have on the spatial domain. Then there is no time domain aliasing when you are doing inverse DFT and all, is it not?
Yes, sir, but what about a periodic signal itself? Like if a signal is itself periodic,
Hmm.
and if we do the sampling in the frequency domain,
Hmm.
then anyway it's going to return after certain intervals of time, right?
So,
Assuming that there is no
right.
time domain alias.
Yeah, think about it this way. Just like you have Nyquist theorem for telling you which is the rate at which you could sample the signal, what is the rate at which once you so there it is a band limited signal is the condition to avoid frequency domain aliasing, correct? What is the conditions to avoid spatial domain aliasing or time domain aliasing?
So the periodicity should be like twice the length. Should be equal to the length.
Yes,
Greater than or equal to.
that's right. That's right. So the moment you are considering what is the size now there, it is m by n size, or you take a simple time domain signal, 1D signal, okay, which is discrete. If you have n points there, as long as you are taking n point DFT and inverse DFT, you will not be introducing any time domain aliasing. Is that correct?
Yes, sir. Yes, sir.
So does that answer the question?
Yes, sir. To some extent, I think I'll work it out myself and see.
Yeah,
once.
maybe you could maybe you could rephrase and tell me again. Let's think about it, because that's a very good question to see when there will be an aliasing, what should be the length there.
Yeah, so I was thinking like if anyway if we have a periodic pattern present in an image, and or a periodic signal in general if we have even in 1D.
Okay.
So just taking one period of it and trying to analyze the inverse CTFT, the inverse DFT. So that will anyway repeat, like even if we consider the whole signal, it will repeat after certain intervals of time.
Okay.
But this signal is itself periodic. So whatever is getting aliased, we can we can reconstruct it back just from the single period present in the signal, right?
So is it what you are saying is, can we not go below m by n sampling? That's your question, is it?
Yes, sir.
Yeah, see, in specific cases that is always possible. What we are looking at a generic case is what are the number of points of that you need to consider in the frequency domain, such that in general, irrespective of what the content you have in the discrete time domain, you have no aliasing happening in the time domain when you are taking the inverse transform. But as you rightly said, if that signal itself is having periodic, then that signal could be in a way that when there is a time domain aliasing also, those components are zero essentially. So that case, even if they are overlapping, it is not going to affect your signal.
Yes, sir. Then it makes.
Yeah, yes. That is possible. That is possible, because time domain aliasing, if your coefficients are zero there, okay, whatever you have the signal, then it is possible. Right. Any other questions here?